Today we are going to hear a talk by Tanner. Tanner Johnson is a first-year PhD student right here at UT Austin. Originally from Hayward, Wisconsin, Tanner completed his BS in geosciences at the University of Arizona, where he researched post-fire debris flows and post-fire runoff with Dr. Luke McGuire. At the University of Arizona, Tanner won Best Undergraduate Talk for his work on modeling post-fire debris flows under climate change scenarios, which is this talk that he will be giving us. During his PhD, Tanner will be working with Dr. Danielle Tuma and Dr. Joel Johnson on post-fire hydraulic hazards in a warming climate by looking at climate extremes using a variety of methods. So we're looking forward to your talk. Thanks all for coming, and take it away.
Thanks for the introduction. I really appreciate it. Thank you all for coming. But as a part of my senior capstone project at U of A, I conducted a pre-fire assessment of post-fire debris flow hazards that was in a watershed near Flagstaff, Arizona. So this talk is highlighting what I learned from this project and as well as some cool data that we gathered. All right, so in the middle of June, specifically June 12th, the pipeline fire occurred in about northwest or northeast of Flagstaff, Arizona. It wasn't contained until over a month later at the end of July. And the infamous Copeland debris flow, for those who are from Arizona, it was initiated in the middle of July, so it was before the fire even was fully contained. So this really emphasizes the fact that pre-fire assessments cannot be or need to be done before the fire is even put out, because these cascading hazards of debris flows happen to reoccur more often than not. And especially in Arizona, with monsoon season overlapping with fire season, this event basically creates this recipe for disaster for communities that live near the mountains. Can I switch to a different presenter view, actually?
Yeah.
Okay. Guys,
That's a super cool picture.
right? One second.
No.
There's so many Mackenzies.
All right, so let's get back to it. So the main fire effects that we're most interested in learning about and focusing on when addressing these debris flow hazards are decreased vegetation cover, which is pretty straightforward in the name. As you can see in this photo on the right, the total landscape up on the watershed has been completely burned, basically where there's just these giant barren trees that are left. There's no shrubbery, the grass is almost all gone, and all of that kind of piles up as burnt debris on top of the surface of the soil. Next, we want to look at decreased infiltration capacity. So the best way to explain that is imagining rain falling on a rain jacket. So when the fire burns all of the shrubbery and then parts of the soil, it creates this hydrophobic layer of this soot and ash that have been piled up. And when rain falls on it, it won't be absorbed for tens of minutes. So it'll pool up and just run down the slope if it's on a higher elevation. So that, combined with all of the sediment or all of the debris that has been piled up throughout the entirety of the watershed, it'll pick up more and more sediment as it flows down, which leads to the runoff-induced debris flows. And then also it's important to note that increased soil erodibility is important too, because fire incinerates all the fine roots underneath the trees. So that reduces cohesion within the soil, which then therefore leads to easier sediment transport of the soil itself down the mountain. And as you can see right here on the left, there is this completely burned landscape, nothing left. This black color is that soil that has that hydrophobic layer on top of the soot and ash that water is not able to be absorbed into. So when I mentioned debris flows, throughout this talk, I'd like you to envision this type of phenomena. It's a very viscous flow. It flows like concrete up and over these little highs and lows of the channels, and it picks up a lot of sediment, down trees, logs, boulders, all kinds of different stuff in its path. And it's very, very difficult for these things to stop. It eventually just has to be within a low energy environment, near flat surface area once it all gets dispersed. This is one of the debris flows that happened after the pipeline fire that was actually caught on camera, which is pretty cool. Sometimes you get lucky and see it, and it's not an area with homes. There's two types of debris flows. One, the runoff initiated, like I mentioned before, is focusing on, it's more prevalent in the Southwest United States. Then there's also soil creep or shallow landslide induced debris flows, which happen in the Pacific Northwest, where the soil is much more saturated. This head up in the front is practically consisted of all boulders, very, very heavy, high energy transport area. And imagine a home being right here. The first thing you see is a 10+ foot wall of boulders coming toward your house. Nothing can really stop that. So in Arizona, people love living next to the mountains and everywhere else. So not cool. Then behind it is the tail of the debris flow, where all of the kind of mud and sediment eventually gets trailed off to, and it kind of turns into this, or it doesn't kind of, it does turn into this really hard cement-like layer of mud that takes a lot of energy and time to get rid of. And it basically becomes this new layer of where the soil is. This is a great example of the debris flow that happened because of the pipeline fire. You can see the different size of rocks and boulders and various debris that has been brought down from up on the slopes of the mountain, with logs and this whole tree over here being covered. This whole tree being covered. And if this house was 10 yards closer to the picture, the whole first floor would have just been wiped through. As well as the severity of the flow as it goes down, you can see the scars from on this tree, probably 6 to 8 feet high, where rocks have been thrown up and caused some damage on these trees. Another example of this is the Montecito debris flows in Southern California. This is very notable because of the death toll and all of the financial damage that it caused in these areas, with giant boulders being brought down, these homes being completely destroyed and buried, as well as in Colorado, they see it a lot during the mountain, or in the mountain passes where there's highways, and it takes a lot of time and energy, as well as cost, to remove all these debris to get these roads back functioning again. So narrowing back into the area where we specifically studied, the pipeline fire is in the eastern part of the San Francisco Mountain, Flagstaff, Arizona. So again, this is just an image to get back reference into what that looked like. But we're focusing in on the southwestern part of the San Francisco Mountain in the Fort Valley watershed. And the reason we decided to conduct a pre-fire assessment here is because it is right next to the Snow Bowl ski resort, which is the largest ski resort in Arizona. And there's only one road to get there, and it is right there. So this watershed would be the primary watershed that would have the potential to destroy the infrastructure leading up to this ski resort. And our main objective throughout this study is to figure out where the flow will go. What areas downstream will be affected? Will it be a very large area inundated, a small one? Will it flow more to the east or to the west? Those are the kind of questions we're trying to figure out when looking at this specific watershed. Okay. 3 main goals of this hazard assessment are to: 1, how does the area inundated depend on burn severity? So throughout the study, one of the parameters we'll be changing is the percentage of the watershed burned, whether it was 20%, 40%, up to 100%. And then how does this vary with intensity of the rainstorm? So 15-minute peak rainfall intensities are known to trigger debris flows. And we will be changing it from a 2-year storm, 10-year storm, 100-year storm, etc. And what that means for anyone that doesn't know is what is the probability of that event occurring within that time period. I can go into that in a little bit if anyone else needs a little more clarification. And then lastly, we will look at the climate change influence about how area inundated changes in the future with a warming climate. And the reason that we're doing it as a pre-fire assessment is because we don't know when this fire is going to burn, whether it's tomorrow, 5 weeks, 40 years. We need to help better prepare the communities in this area for when it does burn, or if it burns. And I would also like to mention, less precipitation in this instance does not equal intensity. So you could have a 1 hour long storm, but that doesn't equal the intensity of the 15-minute period. And we're mainly focusing on this 15-minute intensity period. First question that we need to figure out before we enter it into the model is how big will the debris flow be for the volume? So the constant in this situation will be the terrain because we're looking at the same watershed. So this is the debris flow volume equation within the USGS. And the relief does not change, so it's the same elevation change. Then we'll be looking at the fire. We'll be changing the percent of the watershed burned, specifically at moderate to high severity, because that is also known to cause debris flows or be the influence on debris flows. And then lastly, we'll be looking at the 15-minute rainfall intensity, using the NOAA precipitation data from a rain gauge actually on this watershed. The next question we need to ask is, where's it going to go? So the way that this model works is it takes that volume that we calculated and routes it downstream using a multiple flow direction algorithm, utilizing topography and volume. So this is an example of the model run during the Montecito debris flows that occurred. And you can see how there's different depths, how far it goes, based on from the top of the slope from the initiation point down at the bottom of the watershed. Quick summary of our methods. We now know the debris flow volume. We're going to be adjusting the parameters as needed to check and see what the influences are, utilizing ProDF to route the flows downstream. Then we will be computing that area inundated to check for any differences. And then specifically, we'll be exploring how that area inundated varies with different parameters. So now let's look at some debris flows. With a 2-year storm of about 53 millimeters an hour, if the watershed burned if the total watershed part of the burned at 20%, the total area inundated will be about 1.41 square kilometers. And if the same watershed burned at 100% with the same storm, that total area inundated increases by about 33%. And you can even see within the photos that it becomes deeper at some points. It spreads out a lot further. It almost starts impacting this main highway running through Flagstaff that leads up to the Grand Canyon. So even just the weakest scenario in this instant with a 2-year storm, 20% burn, it still has some pretty severe impacts to this road, to Snowball, as well as where these homes are down here. Now, we looked at how rainfall intensity changes the effects of debris flows. Keeping the percentage of the watershed burned at constant 100% at moderate to high severity, we analyzed how the changes from a 2-year storm to a 100-year storm affect the watershed. And it increases by about 145% the total area inundated. And the reason there's this kind of square cutoff is because the model uses like a grid system, but you can imagine how much further it would go based on the depths at the edges. So this increases by a ton based on the precipitation intensity of a storm if this were to occur. Now we need to figure out, how does climate change influence post-fire inundation? And in order to answer that question, we wanted to estimate how reoccurrence intervals or rainfall intensity changes in the future. So in order to do that, we use the Martel et al. 2021 study under the RCP 8.5 scenario, which uses the reference rainfall intensity that we previously had, change in temperature, as well as the rainfall scaling factor based on the Clausius-Clapeyron equation. And that gives us our future rainfall intensity. So that same 2-year storm will change from 53 millimeters an hour to 76 millimeters an hour using that climate change scenario. And the total area inundated increases by 38%. So in the future, when we have a typical 2-year storm, which happens fairly often, the total area inundated increases by quite a bit. So this is what we kind of looked at with the same storm analysis. And now looking at the climate change scenario for a 25-year storm, it is almost the same as a current 100-year storm. So that highlights the fact that in the future, it'll be theoretically, quote, easier to have a larger debris flow based on the precipitation than it would be today's world where it's in a 100-year storm. Does that make sense to everyone? We'll make sure that, okay, good, explain that well now. So you can see just how large these can get. I mean, that's just fascinating, I love it. But in conclusion is that total area inundated is able to increase by about 33% while increasing just the percentage of the watershed burned. Then it's about 146% of the watershed or of the increase of the total area inundated when changing the precipitation intensity. And then at our site, the rainfall intensities increased by 1.4 by the late century. And this highlights the fact that effects of climate change should 100% be accounted for during pre-fire assessments in order to get the best picture about what could happen. Because if that fire happens in 100 years, it's not going to be the same data that it once was. Now, graduated from U of A, came over to Jackson School of Geosciences, toured with Danielle Tuma and Joel Johnson, where I'll be studying post-fire debris flows again, but with more of a climate emphasis. And I will go into that in a little bit in a second. So I will be presenting a poster at AGU this December, talking about how or analyzing the drivers of Western North American wildfires, looking at all kinds of different drivers of those, whether it's drought, precipitation, etc. But still in the very much so the beginning of our work. Looking for any trends or hotspots within our data. That's the big thing that we're looking for right now in the preliminary stages. And we also want to include atmospheric rivers within this talk as well, because that'll probably be what one of the potential chapters of the PhD will be. Within this data here, we analyzed how the latitude or fires are occurring by latitude from the early part from 1984 to 2003 and 2004 to 2022 using the monitoring trends and burn severity data. And then also here on the right, these are two figures that we plotted just to see how the area burned excuse me, lines up with the number of fires in total. So pretty interesting stuff right away. I'm excited to keep working on this. And the big overarching fact is that I've learned through this previous project in undergrad that you can't really look at things just from a geomorphic perspective. You need to look at things from a climate perspective, because ultimately it's going to be changing and our new normal will be different, or our normal will be different in the future. And in order to answer these big questions about how debris flows are going to be changing, about how they're going to be stronger, you really need to incorporate that climate aspect, because you never have the full picture when just looking at the dirt on the mountain. So that's basically it. Pretty short talk, but thank you all for listening, and I appreciate it. If anyone has any questions, let me know.
I do have questions. The first one is, I don't really understand about the overall topic, but from this part that, well, from my way of thinking that the wind direction changes, right?
Mm-hmm.
So was the wind directions considered in this study before? Because it's like in one direction.
The wind specifically, no. It was just looking about the after effects of fire. And it wasn't a parameter that we considered, or it wasn't in the model specifically. The model is pretty, I guess, simplistic in the sense that it doesn't include different soil parameters or like different types of data within the inputs. So
The second one is about the model itself, that how many grids did you use for the model? Because it's quite a lot of grids there.
it was just the specific digital elevation model of that watershed. I'm not sure the specifics of the grids or how many there are, but all I do know is that it just used that watershed's elevation model.
This was a great talk, thank you. Have you, can you adjust the models to like know about pre-existing debris flows and how that may change the routing of future debris flows? Is, I don't know how erosive or how the debris flows change with the ones that happened before. I don't know, is that something you looked at?
Yeah, we didn't look at it specifically, but in order to get this model running correctly, we used that pipeline fire and the debris flows that were produced as almost like a calibration. So that debris flow was very well studied and surveyed, so we were able to compare the survey of the debris flows with what the model produced. So you could do that, but then specifically answering your question about if there was debris flow, how would you change it, like the next time? You could theoretically run it for a watershed that hasn't burned, and if it burns and produces a debris flow, you could then route it again with a new DEM, and then see what happens then, if that makes sense.
So for the new DEM, would you have to reacquire the? Did you have, at the end of a model run, like your depth of deposited debris on the map?
Yeah, so we have like the depths here, like peak flow depth, but it would have to be like a brand new DEM, like you were talking about. So I think that answers yours.
Does the model care about like which part of the watershed was burned? And can you put that in the model?
From what I'm aware of, no. I believe it just takes in that equation and then utilizes that. I think that'd be important to do. I know that Luke's now PhD graduate, is still in the fine tunes of working it. But it mainly just deals with like at that and like that initiation point right here. What's the volume and then the topography like below it.
Do you have any concept for what is outside of the box, like 4.51 to 4.64? How much of that is just you're not able to like adequately increase the domain? Like, could it be a whole lot worse than
It would probably be different, but I think it's because using that equation, it has like the volume that it would be. It would just be a matter of like where it would go. But that is a good point, that I do think that if this would not just route it sideways, it would be very different about how far it is inundated. So that is a good point. But yeah.
So this is kind of a two-part question. I'm not entirely sure if fire intensity changes with average annual temperature in a region. I've heard, feel like I've heard that it does. If it does, can you input that into your kind of varying climate scenario models for this forward-looking stuff?
It's a really good question. I would say this just uses, we basically just looked up how much of a watershed. Let me think about this for a second. Because that is a really good question. I would say you probably could, but we basically just use that percentage calculation as like we just calculated the percentage, but honestly, yeah, I don't know. That's a good question.
What kind of parameters did you calibrate? Like when you said you calibrated it for the pipeline fire?
Same ones. So we used the percentage of the watershed burned of that actual watershed. That was because we have that data, what areas were burned at moderate to high severity. And then we used the volume of the debris flow that was produced into the model. And then we just ran it with those same parameters to see if it produced something similar than what actually happened.
Was it quite similar?
Yeah. I don't have the specific number with me right now, but I think it was like correlated like 0.7 R square value, I guess. Not bad. But they did a really in-depth like correlation with the Montecito debris flows, and that one they got pretty close.
How good of a digital elevation model do you need to run these simulations?
This was, sorry, go ahead.
Go ahead, it's just.
I believe this was. 7 or 10, maybe 5 meters. Yeah. Somewhere between there. I can't
So I
remember.
imagine a lot of the, I'm familiar with the area of Northern California that burns a lot. I'm pretty interested to the family up there. I don't know if they have good DEMs, but like a 10-meter, whatever satellite grid, would that be adequate on a large scale for modeling these flows?
I think it just depends on the size of the watershed. Like, if it's a smaller watershed, I'm sure it would be very different than if you had a very large one.
But it also depends on like how, like topographically
Yeah.
different it is.
Yeah, definitely.
As you're looking to like go forward with this, you mentioned you might have a chapter about atmospheric rivers. There's a lot of, like, some people just think their whole lives about rainfall and these high intensity rain events. Like, what are the, what's the direct, like, what are you trying to produce in the end when you say, if we take in these things, we get something, you know, given you have got like this whole world of starting things with all the wildfires, all the debris flow stuff, and all the actual rainfall weather stuff.
I think that's what we're trying to figure out right now, actually. But where I'm thinking this could go is creating like a years with atmospheric rivers and seeing if there was any correlation with the fires in the next season, because there's a lot of data produced about the 1 year delay. So I think it just kind of be right now, just checking to see if there is any correlation between the two in terms of fire season, starting earlier, starting later, ending earlier, ending later. So right now, I think it's just a lot of kind of figure it out as we go. It's a really good question.
So guessing like 5 years before you actually publish any of this, is the atmospheric river, I say, is grand scale climate change gonna have a bigger effect on the fire intensity or the rainfall intensity in terms of like how bad debris flows get?
In terms of atmospheric rivers, the thing that we're looking for is to see, because atmospheric rivers are day-long events of just a ton of water, not necessarily high precipitate or high intensity. So we're gonna be looking at this 15-minute intensity within these storms to see if that changes at all, as well as, what was the second part of your question? Sorry, kind of got carried away.
If the effect of the atmospheric river on the rainfall part versus the wildfire severity and frequency part.
Do you want to help answer that second part of that question?
I mean, I think that's a good question. So my work is mostly in the wildfire side of things, and we do find like in future climate change that wildfire frequency is supposed to increase in the future. And with increases in temperature and more drought, then we would expect like increases in wildfire severity as well in the area. But in terms of relating it to how bad atmospheric river intensity is gonna become, I haven't seen that done, so that would be something that maybe we try to answer, like, you know, where we, what's kind of winning out and what's more, and what's the bigger driver.
Had that as a question, right? Our ongoing question. Thank you for that.
Yeah, I wrote a paper looking at like just the meteorological conditions in terms of wildfires and then extreme rainfall, but not specifically atmospheric rivers. But we find that in the western US, some locations have more influenced by increasing intensity of rainfall, and some other areas are more affected by increasing wildfire risk. But yeah.
Some cool stuff the next 5 years.
I have a sort of, I guess, social impact question related to this, because I was like looking at your maps and like all the scenarios basically showed that that road that you were talking about was going to be covered. So like if there's a wildfire in that area and there's a decent amount of rain, in the future, it seems like that road is gonna be covered. So do you know if there's like, are people sort of thinking about that and saying like, okay, this is how we prepare for this? Like what, like, I guess, can you use your results to then do some sort of like planning to say, okay, we're expecting there to be a debris flow here,
Mhm.
so we're gonna like prepare some sort of infrastructure?
Yeah, I think it totally could. If I had the time to get this published this past year, I think it totally could be like, let's give this to these people
Yeah.
and say like, you need to better prepare for this to happen. But the problem is like, you'd be like, oh, prepare for it, and then it doesn't happen for like 45 years. So that's the really, really hard part with this fire and debris flow mitigation is
Yeah,
preparing people, but the public might be like, well, I'm paying for something that's not gonna happen, and it's very
Yeah.
difficult.
I
but-
drove quick, so I know all about that.
So,
Yeah, cool.
How common are these wildfires up near Flagstaff? Cause, northwestern California are super, super common. I don't know if they're as common.
in Arizona, it depends on the year, but they're becoming more and more common, that's for sure. Especially because you have 2 seasons of wet in Arizona. You have the winter monsoon and the summer monsoon. And in between that is very dry. So you have a lot of potential for fires to occur with a lot of vegetation up in the mountains. You don't really see many fires down low, but I think it's definitely increasing. Do you agree?
Yeah, I mean, I think there were some really massive fires the past few years
Mhm.
over there.
Yeah.
I would second it's broadly comparable to the California, Northern California expectations. You know, Flagstaff is high enough elevation,
Yeah.
it's green enough, it's dry enough, and
Similar climate to parts of
Yeah.
California.
And also like the past few years, hasn't there been like, I think the summer monsoon failed a couple of times as well.
Yeah, I remember this past year,
very delayed.
yeah,
Very delayed.
yeah, like in Tucson this past year, we barely got 2 or 3 monsoons. In the summer, and then 2 years before that, there's a lot more, so it is changing quite rapidly.
Any questions from anyone online? A few people. Questions? All right, thanks, Tanner, great talk.